Viruses have captured our attention for decades, sometimes for the wrong reasons. From seasonal flu outbreaks to global crises like COVID-19, their impact on human life is undeniable. Yet despite their influence, viruses remain deeply mysterious. They behave nothing like the living cells we're familiar with, and in fact, some scientists argue they aren't even alive at all. This leads to an intriguing and surprisingly complicated question. Where did viruses come from? To answer it properly, we need to start with a clear definition of what a virus actually is. A virus exists in two distinct phases. First, there is the virion, the extracellular particle that travels between hosts. In this state, it is completely inert. No metabolism, no movement, no replication. The second phase is far more dynamic. Once a viral genome enters a host cell, it becomes metabolically active by hijacking the cell's machinery to make more copies of itself. Traditionally, biologists defined viruses largely by their virions. The reason was simple. Virions are easy to describe, easy to classify, and easy to observe. But that convenience came at a cost. It downplays the most important part of the viral life cycle, and frankly, it's a lazy way to think about what a virus does. A more biologically meaningful definition focuses on the intracellular stage. So we propose the following definition. A virus is a genetic system that propagates by parasitizing the molecular machinery of other cells and disseminates its genome through inert particles. A traditional theory for the origin of viruses was that viruses came before the first cell, or in other words, a pre-cellular world. But our revised definition makes this impossible. If a virus must parasitize cellular machinery, then viruses cannot predate the first cells. Their origin must come after the appearance of cellular life, therefore effectively disproving this theory. From this we infer that viruses originated from ancient cellular lineages that existed after the first cells evolved, but before the divergence of the last universal common ancestor. This idea is supported by the abundance of virus-specific genes. Genes found in viruses but not in any known cellular lineage. Their existence hints that viruses diverged early, evolving before modern cells became, developing many viral unique genes. The hybrid model suggests that viral nucleic acids supposedly formed in a precellular world, lay dormant, and only began behaving virally once cells appeared. The anomalies like giant viruses were explained through the frequency of gene capture, gaining additional genes from host cells. However, there are several flaws. Firstly, there is no need for precellular viral nucleic acids. If viruses evolve between the first cell and LUCA, there is more than enough time for them to accumulate unique genes without resorting to precellular origins. Secondly, parasites tend to reduce their genomes as they try to minimize cost of the bigger genomes and maximize the value of parasitism. Therefore, gene capture provides zero evolutionary benefit, making it counterintuitive. Furthermore, giant viruses like Pandora virus contradict gene capture. Over 90% of their genes do not resemble cellular genes. If gene capture were extensive, we would expect the opposite. Thirdly, the gene pool pattern of viruses doesn't fit the gene capture model. If viruses gained genes from cells repeatedly, we should find a universal viral core plus additional genes. But we don't. Instead, viral genomes display a patchwork of unrelated genes. This patchiness contradicts gene gain from gene capture, whilst simultaneously providing an interesting viewpoint on the potential of gene reduction for the origin of viruses. This brings us to the most compelling explanation, the reduction theory. This model proposes that viruses began as cells, or at least as cellular lineages, that gradually lost genes over evolutionary time. As they became more dependent on their host, their genomes shrank, leaving behind only the essentials needed to hijack others. This theory elegantly explains the patchy viral gene networks, as different cells lost different genes to form viruses. The viral-specific genes, early divergence before LUCA allows unique gene evolution. And giant viruses, instead of forming from gene gain from capturing, they could simply be cells that retained more genes instead of losing them. However, there is a major challenge. It seems unrealistic for a cell to shrink all the way down to the simplicity of a modern virion. But this objection only holds if we make the mistake of defining a virus by its virion, which we established is wrong. Here's a more realistic scenario. Early cells regularly secreted vesicles containing genetic material. Some vesicles contained genes that accidentally replicated alongside the host genome. These genes benefited from parasitism. They replicated without doing any metabolic work. Over generations, natural selection favored gene variants that produced better spreading vesicles. Thus, vesicles got more and more complex, whilst the original cell lost more and more genes. Eventually, the vesicles became fully autonomous virions. The host cell, now completely redundant, could collapse and go extinct, leaving behind only the parasitic genetic systems, early viruses. This bypasses the unrealistic idea of a cell shrinking into a virion. Instead, the transition happens through vesicle-mediated replication, which is much more likely to occur. Ultimately, we can never know how viruses came about, we can only speculate. The reduction model is currently the most plausible. In the future, who knows what exciting new analysis techniques could be used to determine the origin of viruses. Thank you for watching. Like and subscribe if you would like to see more videos like this.